Welcome back, guys. I'm going to try and see how things work out with a new type of video series or like type, let's say, where I'll just read through technical articles, or I'm even thinking of doing this with research papers, breaking them down and introducing new ideas, especially those that align with my own research or interest in general. um, whether like you do academic stuff or you are just a software engineer or senior, middle, like level or junior. I think it's always just nice to discuss different ideas. I thought this would be a good space to like recommend things, also get feedback, suggestions, and also maybe dive into more discussions and see what you think as well. And for this first video, I found this article quite interesting and a nice read actually, by Matthew Prast. To be a better programmer, write little proofs in your head. It's not going to be like a mathematical proof things. It's actually like much more easier, as we'll see in a bit. But it's just like interesting, and I think it touches on a very like a higher level idea of like when you want to write something, you have these designs or logical steps kind of done in your head, or sometimes even you might sketch them out on a piece of paper or whatever, and then actually start implementing, because it does make a difference based on my own personal experience. Regardless of what field or what type of programmer you are, it's always nice to just get things right on paper and then move on to like implementation. And so yeah, let's just dive into it and see what it says. So it's a brief write-up of a trick that helps me write code faster and more accurately. So it's like a trick, it's something he's noticed as he's gotten more experience in his career. When you're working on something difficult, sketch proof in your head as you go that your code will actually do what you want it to do. A simple idea, but easier said than done. Doing this online without interrupting your flow takes a lot of practice, but once you get really good at it, you'll find that surprising amount of the time your code will work on the first or second try. Is a lot, I guess. Feels a little magical. Yeah, this just comes back to what I was trying to say, and it makes sense. Like there's 2 points here. One is like it takes a lot of practice, and it just comes through experience, right? A lot of the things, the intuition you build or the gut feeling, it just doesn't happen with, let's say, reading this magical book, and then when you read it or you take that course, you suddenly become like this, like high level or very senior engineer. It just takes effort, practice, and a lot of work. But once you get there, you realize how valuable the journey has been. And the second thing is the point that like your code will work on the first or second try. And I want to like reiterate this because based on my own personal experience, like I remember we had this embedded systems project, and I worked with a partner on that, and we like before that I usually just coded, and basically my partner introduced me to this different approach that where he literally just wrote pseudocode on paper for this like embedded system program, which was like event driven and stuff. And it was like maybe 2-3 papers that were completely written, from start to end on both pages, on both sides. I mean, and then the thing was, which was very invaluable for me, was that we got like the code right maybe 70-80%, and there was lots of code, like it was hundreds of lines of code when you actually started implementing, not just pseudocode. And we got it right in the first try by like a rate of maybe again 80% or something. Before that, what I used to do was just code and then just test it and see where the bugs are at, like do another iteration and so on. But this one kind of gave me a different approach, which was nice, and I think you should try it. If you have not, I'll definitely say it's a nice thing to do. Now, In this like article, he goes through a few examples. The first one is monotonicity, and basically it discusses that like some things are, or some parts of the code or functionalities are monotonic, and it basically means that they move in one direction. That can go like mathematically, right? We had if you've taken in math courses, we have increasing monotonic function, or stays the same, which is yeah, and decreasing ones. So like something like this, we call this like monotonically increasing, right? Or something like this, or decreasing is something like this, right? And but like I think it's just more informal. It basically means that the process or whatever the design you have, it proceeds in one direction and one direction only. And it brings up the checkpointing example. So you have a script that performs multiple tasks in sequence. You keep a bit of the state around on disk. If something goes wrong and your script crashes, it can check the on-disk state to figure out how far it got, then start again from the earliest state. I mean, checkpointing is actually something that you'll see, especially in distributed systems, is one of the like go-to methods for ensuring like consistency and even fault tolerance. Speaking from my own experience, we actually had like this pipeline that we needed to design. It was for like bioinformatics data, and so like in the pipeline we had like some specific files that needed some analysis using bioinformatic tools, and I think they even involve some like machine learning or deep learning type of approaches, which I wasn't so much familiar. But like the from a systems perspective, right? The pipeline had multiple steps, and like we got some file. Then we started pre-processing, like let's say phase 1, then phase 2, and then like phase 3, and then an output, right? This is not good. So we got the output, and since we had these like 3 steps, let's say, we used temporary files, right, in the servers, and wrote the state after each like phase was completed. Like here we would have one checkpoint, and here we will have another checkpoint. So when if a server crashed, right, in the analysis like servers, like let's say in phase 2 you had a crash, what you would do, the way we implemented, we would go back from this state and start again and try to do phase 2 again. Without that, we probably needed to do all the things from the beginning, from here, but you know, it's not really nice to do that because it takes a lot of time. In general, it could even go on for a few hours. So we just go here. So instead of doing that, we had this like splitting of concerns and trying to think of a smart way of dividing the analysis process into multiple steps and having checkpoints here and here, such that if there was any problems, we had some sort of checkpointing and like idempotency. And yeah, so like I guess this is one example of a monotonic, let's say, proof. And it brings an example of like LSM trees. Like again, it just talks about like journaling file systems. Like we had some videos about file systems, but I never got into the like journaling ones. Maybe I'll make some videos about those later. But yeah, so activity log is a simple idea that often pops in surprising places, like journaling file systems and database write-ahead logs. LSM tree, so it's one of the types of like indexes that databases can have. Are used in some to store rows in memory and on disk, and most of the time they are purely additive. Put loosely, an LSM tree keeps a log of all inserts, deletes, and updates, and scans the log to reconstruct the appropriate value of the row when the row is read. Stale operations are periodically discarded to save space in the process called compaction. The space taken by an LSM tree only grows, except during compaction when it only shrinks. So I guess since it's an again additive kind of a database, right? You keep like you stack things, and you always have logs of what's happened, so you could reconstruct things going back. It's similar to checkpointing. So I'm not really familiar with LSM trees, so I can't really speak of experience. But compare this to a B tree, which is more traditional. At least and updates rows in place, right? This is the important part. B trees generally have to do a lot more work to reclaim the freed space after a delete row and make sure things are. Yeah, okay. So I'm not so much into like B tree and like how they. I've forgotten actually how B trees work, but I guess it just basically means that like LSM tree probably has more logs and tries to reconstruct things going backwards. And again, I think the monotonicity is like it's just you keep adding things. There's only a special case of compaction where you shrink stuff to preserve memory or space, disk space, that is. And then it talks about immutability as another theme of this. When you create an immutable object, that object cannot be modified, that's for sure. Values can be assigned to an immutable object exactly once at the time of the object's construction. You can't back out or undo the assignment. That's very much correct. This allows you to ignore out of hand or scenarios in which an object might change out from under your feet. Yeah, I mean we know about immutable objects most likely. So in Python, tuples are immutable like data structures, right, or data types in this case. You assign them, you can't really change them. If you want to make any changes, essentially you need to create new tuples with the updated values or whatever. So like I guess you could also think of it of some like state machines where you have like state 1, let's say, actually let's put it this way. So you have a state pending, right? Let's say we have a scheduler, right? You have like a job assigned, a job created, and then you first put it in the pending state, and then you say, okay, let's go to the start state. But there's like let's say in our scheduling mechanism we don't have anything that goes backwards, so this is not allowed. I guess this would count as a monotonic kind of code or mechanism, right? Because you only can go from a pending state to start, and when a job starts, I guess like it should only be like stopped when it's finished, right? So you have this like very monotonic way of approaching things. Of course, it could be different ways depending on how you implement or what design you're going for, or what guarantees or properties you want your scheduler to have, but that's just like one example I thought of about this. So the next thing is pre and post conditions of, well, functions more specifically. The preconditions are basically things that are assumed to be true just before the function runs. Basically, the state of the program we assume that the program is that exists before we run a specific function, right? And the post conditions, well, is basically what's going to be changed, or even what value the function will give, right? Are things that are assumed to be true after the function returns. So I guess, I mean, it's very obvious actually. They even like the author does point this out, but I think the point he's trying to make here, or in general with this article, is that it's good to actively think about these things, like intuitively, as you're coding and trying to within your flow try to think about these things. It just makes coding much more, let's say, I don't want to say simpler, but like the results you get will be much more of higher quality, let's say. And yeah, I think it's like very obvious actually. I won't stay on this one for too long, but what he talks about here about unit tests is very important, I think. And like when you think about when you're adding some functionality, trying to decompose it into like the functions that it has or the variables, and think of it of how you're going to write tests. Like, I've even like seen people who actually start writing unit tests for some feature they want to add, and then in that unit test they have some assertions before and after they call a function or series of like related functions, just to make sure things like they say that this is what the result should be. Now we'll go and implement the functions based on how the state should look like before and after we run some function, or maybe a chain of functions, one after the other. So the third thing he talks about is invariance of a piece of code. Um, so let's see what he's talking about here. Basically, invariance means like a condition or a property, right, that should always be true before, during, and after the code runs, no matter what. So, I mean, you've probably seen this concept like a lot in different like aspects of computer science or software engineering. Um, like, for example, let's say in compilers you have garbage collectors, and in garbage collection, right, it tries to look for variables. Let's say we have a variable 1, and in a very simple implementation you have reference counters, or reference counter like 1, not 2 or multiple. Let me delete it. Okay. And the thing about it is that it's always going to be like non-negative, right? That's the invariant here. So if anywhere in your code, like if you have like unit tests or whatever, you see that your reference counter for any variable becomes negative, you must be 100% sure somewhere you are messing things up. Like there is a bug in your code for sure, because it just doesn't make sense for the reference counter to be negative, right? Usually, like if it becomes 0, you delete this variable as it's garbage now. But like if you have like multiple pointers or whatnot, um, using this variable 1, or like let's say, I mean when I say variable 1 here is like basically some location in the memory, right? This will increase to like 1 or 2 references, and then if you like you lose those references, it hits 0, then you will delete it in like in one sweep of garbage collection whenever like it periodically checks for it. So here it also talks about consistency in terms of an invariant. So this data structure is consistent and valid. You need to prove to yourself that the code preserves that invariant at every point, no matter what happens. An easy way is to divide your code into atomic steps and to prove that each step preserves the invariant on its own. Then you can conclude that the invariant will hold no matter which steps run or the order that they run in. Okay, I think we can, like, an example that comes to my mind is a binary search tree, right? So in a binary search tree you have, I don't know, a node, let's say a parent node with some number, let's say 4, and like the guarantee that the binary search tree is that a left subtree will always have numbers less than or equal to this parent, and the right subtree, so like this could have its own nodes here, right? This is like the subtree on the left side, and you have this, I don't know, let's say 5, and it has its own like tree and etc. On the left, on the right side. So the invariant in a binary search tree, right? And then you have like operations, increase, or sorry, add, or delete, and probably like something like update as well. I'm not really sure, but I think this makes sense, right? So this invariant of the left subtree always being less than or equal to basically the parent, and the right subtree being greater than, you know, the parent will need to always hold. Otherwise, your binary search tree will not make sense. It's not even correct, right? It's not even a binary search tree anymore. It's like something else. And I think when it says atomic steps, it's basically making sure that all these operations, um, when you like basically run them, they will not change this invariant, right? In your implementation, you must make sure that your add function, your delete function, or update function will do the necessary changes within the tree to make sure this invariant is true. Now, in here, it just goes through some example. I won't really go through it. It's just like an accounting example, which I don't really make sense of, to be honest. I'm not really into accounting. Another way to maintain certain kinds of invariance is to use a listener or a lifecycle method, okay, to make sure the invariance stays true at certain critical points. I mean, it makes sense, actually. This technique is often used with multiple pieces of state that need to be kept in sync. For example, C++ uses constructors and destructors to ensure that any memory an object needs only remains allocated while the object actually exists. Right. Use effect does something similar for React components. Okay, I kind of get the gist here. So yeah, but like so like in C++ you have like constructors and destructors, and if you implement it yourself, as far as I can remember, right? Well, then you can define more custom things, or like handle like a more let's say sophisticated object which might have its own objects and whatnot. But if you don't, actually, it has some default one, right, by that's implemented, which may not be optimal, by the way. You might have some memory leaks if you have, again, a sophisticated object. I don't remember so much about C++, but this is something I kind of vaguely remember, so correct me if I'm wrong. And the next thing they talk about is isolation, which is, I mean, one of the biggest like concepts that we probably know about it a lot. But again, I think the point is to try and actively think about it. Like when we want to design things, we have to have the right amount of abstraction and try to isolate different components as much as we can, to make things easier, especially considering that software, like it's interleaved process, you know, it always needs changes, updates, bug fixes. So it's better to have more isolation as much as possible. At least in most cases, maybe there are some instances that you can't do that, or it's better to not have isolation. But in general, that's something that I guess, we all know about. So, so here he says that he's had this conviction that a lot of the craft of software is centered around modifying or augmenting an existing system without destabilizing anything, which is very true, actually, right? When making modifications, it can be exceptionally useful to know how to prove that behaviors you didn't intend to change when in fact left unchanged. Yeah, that's very much right. There's a technique I rely on a lot to prove this. I'm not sure if there's a name for it, and I perhaps wouldn't even call it a technique. But the best way I describe it is every change has a blast radius. A change to one part of the code may necessitate a change to another part to ensure the consistency of the whole system. This second change might require a change to a third part, and so on. Nailing down what behaviors a change doesn't affect, or does not affect, involves identifying structural firewalls that can prevent a change from propagating past. It's kind of like a conceptual cousin of encapsulation. And then, so it tries to give a like very long example. I won't go through it for the sake of brevity, but I mean, I guess one way to think about this is like if you have a function, if you have a program like this where you have like the integer y, you have a function f1 which takes as an x, and in the function you have I don't know, y equals x plus 1, and then you return y or something, right? you have a global variable here, right? If you make any changes to y, um, you're gonna mess up the whole program actually. So like uh, the blast radius is going to be the whole program. Whereas if you have like this function, if you have this other program where you have just the function x, sorry, f1, and then you have an x, and inside it you say integer y is equal to x plus 1. So you just declare it locally, and then you return y here. I mean, it's just a very simple example. It might not be even making sense in what you write, but I think that's basically the gist, right? I don't want to spend so much time on it. It's very obvious. And inductions. I think, yeah, so lots of interesting programs involve recursive functions or recursive data structures. Depending on the area you're working on, you may come across recursion constantly or only occasionally. Yeah, I mean, recursion is one of the biggest things in computers. You just see it everywhere, essentially in data structures, even in like lower level stuff, like in computer architecture and stuff. The way functions are called, in general, you have this like activation frame, right? Where they recursively keep like stacking. They stack on top of each other when you keep calling functions from another function. A recursive data structure is a structure that contains a copy of itself. This copy can contain a copy, and so on, at a base case, right? I mean, if you've basically programmed, you probably know about recursion anyways. If you've taken formal education in like CS or software engineering or even maybe electrical engineering, you most likely have seen this stuff even in a much more mathematical way. Trees are one of the famous examples, right? We talked about the binary search tree in the previous section. It also says lists can also be formulated recursively, but we don't usually think about them, right? But it is very true actually. Like if you have the lists represented as like linked lists, right? It can be thought of a recursive data structure, especially if it's like a circular one, right? Albeit, even if it's not circular, it's still recursive. If you want to like write a function to traverse this, a very elegant function will be recursive. You can also do it iteratively, but I guess it depends on what you wanna or which one you prefer. But even in different other representations, it could be that as well. Like if you've worked with like Haskell or any functional programming language, you would see this actually. The way they like add items or append items to a list recursively. Like there is this book called The Little Schemer. It's a very nice book actually. It's basically teaching you some very like niche language called Scheme, which is a functional language. I think it's like based on Lisp, if I'm not wrong. And the book is all about kinda, you can think of it as a way of teaching you recursion. And there, like one of the parts I remember very vividly was basically how lists would work recursively, and you can have like a data structure lists which works completely recursively instead of like iteratively that we are used to. And then here it just goes into like the mathematical idea of induction, which I mean, if you have taken any discrete math course or are into these stuff, you probably know about induction and how you do inductive proofs. It's actually very beneficial. If you haven't, I would advise you to go through it and learn about it a bit. And here is another example. I'll just keep it short and won't want to dive into the bigger details of this. But if you want to read the article in more detail, feel free to go ahead. And so the next thing, proof affinity as a quantity metric. In this part then, so Matthew basically kind of gives a metric of how to kind of like maybe judge your own code in a good way. So he says basically what I said talked about is to write little proofs in your head about your code. But a dual version of this post, or like the reverse way, is that you should try to write your own code in a form that's easy to write little proofs about. So you write the code and try to think about whether like it follows any of these examples, or maybe even more examples. Like again, he doesn't. I don't think he claims that these are like an exhaustive list, right? It's just some of the things that has grown through experience and has realized and wrote about in this article. So look for monotonicity and immutability. Write code is monotonic. Yeah, keep track of. Yeah, I think this is one of the most easy, like one of the easiest ones, and something that you could always identify and think about when you want to write functions, especially if it's going to be a deep, sophisticated function. You can prove a function maintains an invariant by proving each unit of work does. You should subdivide your code into the smallest possible units that can maintain the invariant. Okay, fair enough. Pay attention where component boundaries act as firewalls that prevent change propagation. Build as many of these firewalls and take advantage. And use induction to prove things about recursive functions incrementally instead of all at once. I mean, going back to induction, one of the things that I want to point out is that, like, one of the common themes again that we see, right, in programming is breaking bigger problems into smaller problems. Sometimes when you do this, actually, you do realize there's a recursive relation. But in the more general case, this might not be the case. Like, this might not happen. You can try to think of a simpler example, but then there is no recursive relationship between them. But it's always good to break more complex stuff into very simple stuff, try to get those right, and try to move forward with it. If it's recursive, great, you could actually have some even a mathematical framework for it, but if it's not, I think it's not such a big deal anyways. And so this is pretty much it actually, and let's see, actually, the idea is that you can judge the quality of your code by the ease with which you can reason about it. I think that's a key point here. Fair enough. If it's easy for you to prove to yourself that your code is correct, it's probably pretty well designed. On the other hand, if it's consistently frustrating or difficult, you should consider cleaning up or restructuring your code to make it more straightforward. He talks here about why, like, he says proof affinity, not provability. I think it's a different concept. As the suggestions above show, it's possible, at least subjectively, design for maximum proof affinity. It says it's not the only dimension, of course, but it's one important one. In order to build, augment, and improve or test your code, you have to understand what it does, what it doesn't do, and what it could do. I would even say that maybe you should make sure what are the things that it shouldn't do at all, right? And as mentioned, this type of micro reasoning only starts to pay off once you can do it without really thinking. It's a little like typing that way. Knowing how to touch type only saves you time over hunting and pecking when it's basically instinctual. In both cases, developing your intuition requires practice. Yeah, going back to the first point I made, and I mean pretty much we can all agree on this, right? I was practicing and practicing for hours, days, months. I think the best way to do this is to write more mathematical proofs. I mean, that's an interesting take actually. Writing proofs about programs will definitely help, but I think the simple act of constructing proofs on any topic is a great way to hone the kind of logical thinking that will serve you well when working with complex systems. But you have to write them and not just read them. Okay, writing. Do the exercises. For my own part, I started doing mathematics for fun a while ago, and I've noticed that writing proofs can help me improve my clarity of thought in a broad array of settings. If you don't know where to start, So he goes with an undergrad algorithms course. edX, lead code is also another thing it talks about. Um, yeah, I mean, doing algorithmic problems is always nice. I would definitely agree with him on like doing proofs. Like even if you don't take a course online, like another thing you could think about, or I would suggest is like the book, the very famous book CLRS, right? It's an algorithms book, but it's very mathematical heavy. It has proofs. I would definitely advise you to try and go through um, the proofs of some of the very famous algorithms. Let's say, for example, DFS or Dijkstra, and try to really reason about why, how the proof works. Right? I think the graph algorithm ones are some of the easiest ones to understand because it's not so much mathematically heavy in terms of notations, and it's very logical actually. Um, why, for example, Dijkstra guarantees the shortest path, even though it's like a greedy step-by-step algorithm. And yeah, this is basically the end of the article.